All right, let's look at a few more examples of our parametric equations. So in example 4, we again want to find the rectangular equation for the curve whose parametric equations are x is equal to cosine of t, y is equal to sine of t, and we have the domain restriction that t is between 0 and 2 pi. Okay, now again, it doesn't actually ask us to graph this, and we do not have to graph it, but I'm just going to go ahead and graph it anyway, just so that we can sort of see a visual of it. But if this were a test question or something and the directions did not tell you to graph the equation, you certainly do not have to. I just want to show it to you along with the rest of the process as well. Okay, so if we want to graph it, then we would pick some t values to plug in. In this case, our t's need to be between 0 and 2 pi. I'll just pick easy numbers. I'll go 0, pi over 2, pi, 3 pi over 2, and 2 pi. And we just need to plug those into both of our equations to find our x and our y. So cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is -1, cosine of 3 pi over 2 is 0, cosine of 2 pi is 1. Those are our x's. Then sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is -1, and sine of 2 pi is 0. Okay, so those are going to be our x's and our y's. Okay, so let's go ahead and just plot those points. So we have 1, 0. Oops. Let me add some numbers back to my scale. All right, so we have 1, 0. We have 0, 1. -1, 0. 0, -1, and then back around to 1, 0. So you can pretty clearly see here that we just have a circle centered right at the origin, right at 0, 0. And then if we think about the direction that we're going here, our first point was 1, 0, then we went 0, 1, -1, 0, 0, -1, back around to 1, 0. We're just rotating around counterclockwise on this circle. Okay, so that's what our graph is going to look like. Okay, now in terms of finding the equation, there's a couple different ways that we can do it. Okay, so you can use the fact that we just graphed this. We know what the equation looks like. We know it's a circle, and we know from what we've studied with our conics what the equation of a circle should look like. So we can see here that this is clearly a circle with its center at the origin with a radius of 1. So if we think about finding the equation of a circle, we would just come up with, well, our circle in general is x minus h quantity squared plus y minus k quantity squared is equal to r squared. Well, plugging in our specific numbers, we would get x squared plus y squared is equal to 1. And then thinking of our domain, just again, since we have it graphed in front of us, just reading across from left to right, our leftmost point is at x equals -1, our rightmost point is at x equals +1. So our domain is between -1 and +1. Okay, so that's one way that we can find our equation if you want to graph it. Okay, now if you want to skip the entire process of graphing it because it didn't actually ask us to graph it, that was just a choice that we made, then you can also do the same thing algebraically. Now the way that you would want to do it algebraically, since we're dealing with trig functions in this case, we're not going to do substitution like we did in the last example, but instead I'm going to think about my trig identities. So since we have just a sine and a cosine here, I know my sort of main trig identity with a sine and a cosine in it is my Pythagorean identity. And I know that sine squared plus cosine squared is equal to 1. Okay, well, if we think about these equations, we don't have a sine squared and a cosine squared, we just have a plain sine and cosine, but that's easy enough. We can just square both sides of our equation up here. So then we can just make some substitutions. Sine squared is equal to y squared. Cosine squared is equal to x squared. And that whole thing is just equal to 1. And then again, thinking about our graph, we can see that our domain is between -1 and +1. Okay, so either way about it, whether you sort of solve it algebraically using your fundamental trig identity, or you use the knowledge of conics that we've been looking at over the last few sections, you're going to come to that same conclusion of that equation being x squared plus y squared is equal to 1. Okay? All right. I'm going to leave example 5 for you guys to try on your own, but I'll post the solutions to it up on Blackboard. Okay. All right, example 6, we are going to find two different sets of parametric equations for the rectangular equation y is equal to -2x squared plus 1. Okay, so for parametric equations, basically we need an x equation and we need a y equation, okay? Now, because we're defining these equations ourselves, when we pick our x, pretty much we have the freedom to choose almost anything we want to. So the easiest choice for x would just be to let x equals t. Then we can essentially just make a substitution into our original equation. So if we substitute in t for x, we're going to get y is equal to -2t squared plus 1. So that would be one possible set of parametric equations for this graph. Okay, so just to do another one, instead of letting x equal t, we could let x equal something like t plus 1. Okay, like I said, you can choose almost anything you want for your x value. Okay, as long as it's real, there really aren't too many restrictions. And then again, we would just substitute that in for x in our equation. So we get y is equal to -2 times t plus 1 quantity squared plus 1, or -2 times the quantity t squared plus 2t plus 1, and then plus 1 on the end. If you distribute in the 2, -2t squared minus 4t minus 2 plus 1, or finally, y is equal to -2t squared minus 4t minus 1. So that would be a second possible set of parametric equations. Okay, so if you're asked to convert between rectangular to parametric equations, just pick x equals some simple function of t, plug that into your equation to figure out what your y would be equal to. All right, so the last thing we're going to look at is an application of these parametric equations. And the best application of these is just our projectile motion, okay? So if we have an object that is thrown upwards or shot upwards at an angle of theta degrees to the horizontal with an initial speed of v0, then we can find the horizontal distance and the vertical distance that that object has traveled using these equations. So just to kind of show you what I mean here visually, I'm just saying if we have an angle of theta to the horizontal and we're starting off with an initial velocity of v0, and we might actually even be, say, some distance off of the ground to start with, possibly, okay? Then our x, or the horizontal distance of this object, can be found by taking v0 cosine of theta, so basically the horizontal component of the velocity times t. Our y is going to have three pieces, -1/2 gt squared, that's basically just the gravity piece, okay? G is just our gravitational constant. Then we have plus v naught sine of theta times t, which is just the vertical component of the velocity, plus whatever our initial height is, which we're calling h in this case. Okay. All right, so let's go ahead and take a look at an example. So it says an archer releases an arrow from a bow at 5 feet above the ground. The arrow leaves the bow at an angle of 15 degrees with the horizontal at an initial speed of 225 feet per second. Okay, so we have all the pieces that we need to build our parametric equations. So basically, to start off with, if we want to find our parametric equations, we just plug in the different pieces. So our x, which is just v naught cosine of theta times t. Okay, our initial velocity is the 225 feet per second, and our theta is 15 degrees. T is going to remain a variable because this is a function of t. So we would have 225 cosine of 15 degrees times t. Okay. All right, now also notice our units here. We're given feet for the distance. So between our two gravitational constants, we can either use 32 feet per second squared or 9.8 meters per second squared. We have to make sure that the variables match. So since we're working with feet in our problem, we have to work with feet for the gravitational constant as well. So our g value that we're going to use is the 32. All right, so if we go ahead and plug those in, we have negative 1/2 gt squared, so negative 1/2 times 32 would give us negative 16 t squared, plus 225 sine of 15 degrees, plus our initial height was 5. Okay. All right, so those would be our parametric equations. Right, then it asks us, find the total time that the arrow was in the air. So basically that's asking us, after we launch this arrow up, when is it going to come back down and hit the ground? Okay, which is just going to be as simple as taking our y equation, setting it equal to 0, and solving for t. Okay. All right, so basically just set that equation equal to 0. Okay, all right, and in this case, you would just need to use your quadratic formula. Okay, I trust that you guys know how to do your quadratic formula, so I'm not going to go through the steps of it with you. But if you plug that into your quadratic formula, you're going to get t is equal to 3.72 seconds. Okay, next part here is assuming the ground is level, find the distance the arrow travels before it hits the ground. Okay, find the distance the arrow travels before it hits the ground. So in this case, we already know when it's going to hit the ground. It's going to hit the ground after 3.72 seconds, and we want to know how far did it go before that happened. So that would be looking for the x, the horizontal distance at 3.72 seconds. So for our x, we're just going to plug in the 3.72 for t, plug that into our calculator, and we're going to get 809.26 feet. All right, and then the last part of this says find the maximum height of the arrow. Okay, so there's a lot of different ways that you can do this. The simplest way is just going to go back to your pre-calc algebra, and remember that when we're looking for a maximum, we are looking for a vertex. Now, instead of finding the vertex in the way that we have been with our conics, the easiest way to find the vertex is just to remember that the vertex of a parabola can be found using the formula negative b over 2a, and then just plugging that back in to our function to find the y-coordinate. So negative b over 2a helps us figure out when we're at the vertex, and then plug it into our y equation to figure out what that actual maximum height is. So So negative b over 2a, we'll have negative 225 sine of 15 degrees over 2 times negative 16. And if we plug that into our calculator, we get 1.82 seconds. And then plug that into t in our y equation. Okay, so if we plug in 1.82 for t in our y equation, then we are going to get a maximum height of 57.99, or about 58 feet off the ground. All right, guys, so that is it then for our parametric equations.